and share my screen. Yeah, so just a little reminder of what this paper does. So what the authors discuss is that when we have two-way fixed effects in many periods, where at a certain period some units can be treated or not, the regression that is usually estimated looks like this in Formula 4. So we have time fixed effects and we have some period fixed effects, and look at the outcome. And this period fixed effects, time fixed effects, individual effects, and this dummy. So where E is the time of first treatment and the treatment is assumed to be absorbing. And basically, we estimate effects for different distance from the first treatment period. So if individual I was treated in period 1, then we're going to look at different distances from period 1. And then I don't think they have a graph here. And for some pre-treatment periods and for some post-treatment periods, we will have our coefficient on this dummy variable, which we interpret as the treatment effect. But in fact, they show that it's a pretty weird estimate because it has treatment effects for different cohorts with different weights, and some weights can be negative. And that's the main problem they try to issue, the main issue they try to solve. And we're gonna look at that using the empirical illustration in the paper. And as we move on and look at the data, I hope that it's going to be more clear what all these formulas mean, because conceptually it's actually a very simple approach that they explore. So we are going to use the data from this Dobkin and co-authors paper. The data is available online, and I think, yeah, I link it. There's a link in the problem set here. And a couple of words about the data. So this is a survey, the health and retirement study, where they observe individuals that are hospitalized at some point, and there are a lot of variables, and we're just going to use some of them. So there are several waves of the study, namely 11, and there are so units of observations are individuals, and at some point they get hospitalized. Some of them don't, and we can look at their out-of-pocket payments for the insurance and for their real earnings. And there are some restrictions that we're going to impose. So we're going to look at individuals that are younger than 59. And at and we'll look at waves 8 through 11. So the hospitalization in waves 8 through 11, and pre-hospitalization data are from waves 7 to 11. And we're going to build a balanced panel. So let's look at the study. So here I have a notebook. I'm just gonna use this, but we can go to the R if there are any questions or other issues. So the data file is in Stata format, so we read it using the Haven package. And we can see that there are 387 variables. We're not going to use all of them. But what's important is we have an ID of the person. We have the number of the wave number, and waves are from 1 to 11. We have this EVT time variable, which is time relative to hospitalization. And it's time relative to first hospital. Yeah, so basically, if a person is hospitalized in period T, so this EVT time is the actual period minus the period of hospitalization. So it can take positive and negative values, and this is what is denoted as little l in the paper. We have an ever hospitalized dummy. So if a person was hospitalized, it's 1. There is a wave of hospitalization variable. So this is the number of the wave in which a person was hospitalized. So we have age, well, of at hospitalization. We have male dummies, year of hospitalization, and we have some dummies that denote race, different types of insurance, and our outcomes, out-of-pocket spending, and real earnings. And in our replication study, we're actually going to look at out-of-pocket spending, but of course, everything can be just run for another outcome. And so these are variables from the same variables as in table 2 of the paper. And our purpose is to, well, the first step is to filter a sample the same way the authors do, and to match the means and the numbers of observations they have in this paper and this table. Let's look at, we can do that. So first, they consider waves starting with wave 7. So I'm going to use the dplyr package. I'm not sure whether everyone is familiar with the package, but it's actually pretty simple. I'm just going to explain what it does as we go. So basically, in this block of code, every function is from this dplyr package. And these functions are used to manipulate data. And what we use here is the pipe operator. So let me quickly illustrate this in R. Again, if someone is not familiar with the pipe operator. So for example, I can generate 100 random normally distributed variables, and then I can sum the variables, or yeah, sum their values. And basically what we have here is one function inside of another function. Using the pipe operator, we can write it in a different way. So we write it as in the order in which it's calculated. So first, we generate the random numbers, and then I insert the pipe operator. And of course, in R, everything that is in percentage signs is in a custom operator, and this operator is defined in a dplyr package. Actually, a dplyr package imports it from another package. It doesn't matter. And now I just kind of pass the result to the sum function. And here I don't need to specify the argument. The first argument will be the left-hand side of the operator. And this will be exactly equivalent to the previous code. Okay, so I need to do this first, right? Well, obviously the result is different since numbers are random. Let's generate something non-random so that it's clear. Let's say numbers from 1 to 100, we sum them. Obviously, the result is 5050, and we can do that the usual way or the base R way and get the same result. So that's all it does. And if we use this pipe operator, we can use chains of functions. So we calculate the first object, pass it to the sum function, and then the result can be passed on along to other functions without nesting these function calls into each other, which is hard to read. That's what it's this operator does. And so first, there's a filter function. The first argument is our data set. And then the second argument is the condition by which to filter the observations. So it's a logical vector. And in our data set, we will only have those observations where wave is greater or equal to 7. Next, for each individual, so the next function calls make sure that the panel is balanced. So originally it's unbalanced. What we're basically going to do is drop all the observations, all the individuals that have fewer observations than 5. So we want only those individuals that are observed for all the waves we're interested in, 7 through 11. And then for each individual, we calculate the number of observations. And we do that using this grouping function. We group our data by this function. And then, so the mutate function adds a new variable, ni. And basically what is calculated here is the length of the wave, but of the wave variable. So if we didn't group by, that would be just the total number of observations. But in our case, since we group by individuals, this will be calculated for a particular individual in observation I, and that's exactly what we want. And then we only leave those individuals for whom we have 5 observations. We remove this variable we no longer need it using the select function and the minus ni variable, and just in case ungroup the data. And then we can actually look at how many observations we have for each individual. So the result that we have below is the result of the last statement here. Again, we group by individuals and calculate a summary statistic. So n is a function that returns the number of observations, again, grouped by individuals. And we see the first 10 rows of the data, and at least in these rows, well, there is a number of, yes, with 10 individuals, and for each of them, we have 5 observations. Now our panel is balanced. But of course, we filtered, we now have only waves starting at wave 7. And for some individuals, the hospitalization occurred before wave 7 or during wave 7. We want wave 7 to be our pre-treatment period for everyone. And so we remove all of the observations where the first hospitalization occurs before wave 7 or during wave 7. And here, again, we group the data by the individual ID and calculate the minimum value of this event time. And this is the small l from the paper. And if during wave 8, for example, this variable is 0, EVT time, or the minimum for the given individual, it is 0, then it means that the person was first hospitalized in period during wave 7. Did I say, yeah. or during this wave and to which this observation corresponds. Maybe let me illustrate this graphically. So okay, so assume we have our waves. Well, let's start with individuals first. So we have individual. For each individual, we have 5 waves since we've made the panel balanced. And we have our EVT time variable, which is just the small l. And we're gonna say what it means. So hospitalized during wave. Right, so we'll consider 2 individuals, individual 1 and individual 2. And waves are 7, 8, 9, 10, and 11. Now, well, I say it's, yeah. So if the individual is hospitalized during wave 9, so that's going to be our first individual. We're going to have events time -2, -1, 0, 1, and 2. So this is the distance at the particular moment of time, and the moment of time is wave, of course. And individuals are i's. So in this moment of time, L, yeah, we have the distance to our hospitalization event. And if individual was hospitalized before, say in period 6, then we'll have all negatives here. -1, -2, -3, -4, and -5. Sorry, I think the first one is incorrect, right? These are pluses. The first ones are correct. Oops. No, this is the correct version. And so basically, we wonder if we look at the minimum hospitalization date, we don't want the minimum date be before the 7th wave. And that's why we're going to remove all the positive numbers here. Oh yeah, that's what's incorrect here. Let's look at the so first let's calculate this minimum time, and it's going to be from -4 to 5. And some people are not hospitalized. For them, the minimum function will return infinity. And yeah, basically, if all the values are NAs, it's going to return infinity. And also, it spits a warning. That's what this code does. It turns off warnings. And then we have these numbers of observations for different values of EVT time minimum. So if the person was first hospitalized before our observations, before our wave 7, basically, then we don't want these observations with filter. We want EVT time minimum be negative. Okay, and then there is another variable called wave hospitalization, and this is the wave when the person is hospitalized. Basically, we want, again, the first, so there can be several different hospitalizations, and so we take the minimum, the first hospitalization, to kind of make our treatment absorbing. And so we take the minimum of this wave hospitalization variable and then filter individuals so that everyone's younger than 60. And after we do all these manipulations, the number of unique individuals in our sample is 656. And if we look at this table, this is exactly the number of observations the authors have.
Excuse me, can I ask something?
Yeah.
So the authors say that the treatment is absorbing, but it could also be possible to be hospitalized twice in the during the waves that we're looking at. Is this able to integrate into the model?
Yeah, so that depends on how you interpret the treatment. And in their approach, the treatment is just having been hospitalized. It's not being hospitalized at the moment. It's having been in the past or at present. So if the person is ever hospitalized, they're treated. So that will change the interpretation of the results, but we can define this treatment as absorbing. So if we say having been hospitalized, then of course it's absorbing, because once you're hospitalized, you cannot change the past. Right, so this is basically what we do with the sample. So again, I hope this is clear. We see that this individual will be kept in the sample because the minimum L is -2, and the second individual will be removed from the sample because the minimum L is 1. And this corresponds to the second person being first hospitalized during the sixth wave, and the first person hospitalized during the 9th wave. And this would be actually this wave hosp variable. Okay, so next, what we want to do, and basically, sorry, one more thing. We say that this small l, or EVT time or event time minimum, should be less than 0. So basically, we remove individuals for which our minimum period is infinity. So we remove those individuals who are never hospitalized. And the authors discuss it. They do that so that the parallel trends assumption is more plausible. Because if the person is not hospitalized or hospitalized after or way after all the other people, that can affect the counterfactual outcome. For example, through labor market or just because the person is older. And then maybe those people who are never hospitalized in our sample might not have the same parallel trend, might not have the parallel trends with the people who are in the sample. And of course, the parallel trends are formulated for cohorts, and the cohort being this wave of hospitalization. That's our cohort. So once again, wave is going to be the time period, and wave of hospitalization is the cohort. So because that's the period of the first treatment. And this event time is small l in their notation. So this is the distance to the first treatment. So, okay, well, now we want to calculate these means, maybe standard deviations. So let's look at some of the variables, but I think before that we do period. Yeah, so in our calculations, we're going to use a lot of dummies. So namely, we have cohort dummies and we have these time dummies, or DLs, right? And we also have wave dummies or time dummies. So we're going to later use them in the regressions, but let's generate them now. And basically, if you want to generate a bunch of dummies in R, you turn a variable into a factor. And using the model matrix function, you can. So what model matrix function does, it looks at the formula you have, it sees that wave as a factor, and I don't include the intercept. And so it's going to generate dummies for each value of wave. In this case, wave 7 through 11. And of course, I can't include all of them in the regression because they're, oh, well, as long as I can if I don't include the intercept. That's why I exclude the intercept here so that because I want all of them. So these are the wave dummies. It's just a matrix that we're going to use later. And we also can have the same with for our L variable and for our, so these are DLs basically once we generate the dummies, and for our cohort. And so we see that our Ls go through -4 to +3, and cohorts are 8, 9, 10, and 11. And obviously the seventh wave, we've made sure that no one is hospitalized at wave 7. So this is the pre-treatment period for everyone. And then we can look at the number of individuals that are hospitalized at different waves or admitted to the hospital during different waves. And again, we can choose one of the waves because now we have this wave of hospitalization variable. That's the same for a given individual in each time period because it's the cohort variable. And basically, we just have the number of individuals in each cohort. And we can compare those with the summary statistics, actually. So if we look in the table, these pre-hospitalization outcomes. So, for example, let's start with the 4th cohort. This is our wave of hospitalization 11. Yeah, sorry. We have 65 individuals. And in 3rd and 4th cohorts combined, 228. And again, if we sum up 163 and 65, we have 228, and so on. So again, we have the same numbers of observations in each cohort as in the paper. Finally, we'll look at the variables that the authors look at. So there's the age it was at the moment of hospitalization. So all these dummies that the authors have, we can look at them and calculate means, and in this case, quantiles or quartiles, I think these, and medians. Obviously, we can also look at standard deviations and stuff. So, for example, if we look at the age at admittance, the mean is 56, and that's exactly the same mean as in the paper, age at admission. If we look at the proportion of, say, Hispanic individuals, it's 12.2%, and again, 12.2% is here. Interestingly, that here we have percentages, and in the paper they divide by 100. Yeah, the proportion of those with private insurance, for example, it's 66.16%, and in the paper, that's interesting. Let's see, Medicaid 7.10. Okay, this doesn't look right. I'm not sure why these don't match. So basically everything else reproduces. So yeah, that's kind of a mystery. And then we can look at the outcome variables, but pre-treatment. So the same variables, but pre-treatment. And pre-treatment is wave 7. So we filter that wave. Obviously, now wave is a factor. We did it before, and I have to convert it to character. Otherwise, it won't work. That's a technicality. And so our outcome variable is out-of-pocket spending. and we can calculate the mean. Yeah, and to take one variable, so as a vector from our data set, we use the pool function. And it's this amount, 3,300. Again, if we look at the paper, 3,300 is right here. And basically, we can do that for wave 8 as well. And it's 2,355. And then the paper is 2,355. So the outcome variables on average are the same. So we are working with the same sample. We have the same sample means, except for insurance taxes. Yeah, but that's not something we'll look at, so it won't affect our results further. So these are the summary statistics. Of course, we can calculate a nice matrix, put them there, and also get this kind of table. But I think, yeah, it's clear that we have the same means for important variables and the same sample sizes. So the next question in the problem set is about the graph they have here, figure 2. And what this figure has is for different relative, so for different periods, but relative periods relative to the first hospitalization, the weights of different cohorts. So how to read this graph? We want to, or we are interested in the effect, say in one period, the period 1 after hospitalization. What cohorts actually contribute to estimating this effect? Apparently, there are 3 cohorts. Cohorts 1, so this is our wave of hospitalization being 8. Cohort 3, this is wave of hospitalization 10. And cohort 2, wave of hospitalization 9. And we see that for one cohort, the weight is positive, and for the other 2, the weights are negative. And that's exactly the problem with the simple two-way fixed effect estimator. And we want to estimate these weights of the cohorts. And the weights are applied to the cohort average or cohort specific average treatment effect of the treated. And this is going to be so the weighted sums of these cohort specific average treatment effects are going to sum up to the coefficients in our simple two-way fixed effects regression. And this regression is something that's very typical for an event study. So we include individual effects, the common trends, so the time fixed effects, but we also have these treatment indicators, or the period relative to the treatment indicators. And we're here considering 3 periods before treatment, 2 periods before treatment, and we need to omit some of the periods because otherwise we will have exact collinearity, multicollinearity, and the authors omit the first, minus first period, so 1 period before treatment. And then we have post periods, 0, 1, 2, and 3. So first we're going to estimate this regression, and then we're going to estimate these weights. And the way the weights are estimated is by regressing this interaction. So this is the cohort dummy, and this is our treatment or our relative period dummy. And if we interact them on all of these, we're going to get the weight. And so the idea of the method is that instead of using these relative period dummies, we should actually look at the interaction between cohort and relative period. And that will allow us to estimate our CATTs, but also it will allow us to estimate these weights. And then right, and so the weight omega EL minus 2 means that this is the weight that enters the calculation of mu minus 2. That's the superscript. And the two subscripts are the cohort and the relative period. And so to calculate mu minus 2, we include all the cohorts and all the periods that are, with the corresponding weights. So let's look at how we run this regression. Now we will need our wave dummies or cohort dummies and the relative period dummies and also the cohort. So no, these are time period dummies, and here we have cohort dummies and relative period dummies. And I also include our outcome, individual ID, and not the dummies, but the original. So wave is the time period, the absolute time period. Wave of hospitalization is the cohort, and event time is the relative time period. And since in these variables we have in variable name these minuses, R doesn't really like minuses in variable names, so I replace them with underscores. And to run this fixed effects model, we're going to use the PLM package. It's pretty simple. So the first argument is a formula, and as usual in R, I just include all the variables, and I include explicitly all the dummies I want. So first we have, so this is this D minus 3, D minus 2, D0, D1, D2, D3. These are time fixed effects, our lambda t's. And I just include them as dummies explicitly. And then we have an individual effect, and this is taken care of by the PLM function. So I just specify that the individual index is this individual index, and by default is going to use a within transformation to estimate the model. I could have also specified both the individual index and the wave variable. So for the time index, and then basically the result would be the same. Okay, so if we run this model, let's look at the result of the estimation and compare it to the results reported in the paper. So this is in the next table. So we're looking at out-of-pocket medical spending as in the outcome and at the fixed effect estimator. And let's look at the, well, any estimator. Let's say the authors look at mu minus 2, for example, to decompose it into different cats with different weights. And here it's 203. And what we have is minus 2, 202.6. So rounded to the closest integer, it would be 203. And in fact, all these coefficients are the same as reported by the authors. So they cluster standard errors at the individual level. I don't do that here, and we'll get slightly higher standard errors even. So yeah, this is the fixed effect regression. Now the plan is to generate these interaction variables and to regress them on all the same, basically right-hand side. And then we get the weights that we can plot. And again, we see that the plot here that we want to reproduce, these are separate 4 plots for different cohorts. And we're just going to take one cohort and the first one, and this is the this cohort consists of people hospitalized during wave 8. So our wave hosp variable would be 8, and we're going to get 5 weights corresponding to different periods. And of course, relative periods are from -1 to 3, because in our sample we observe waves 7. This is going to be L equal -1, 8 corresponds to 0, and so on to 11. So this is relative period 11 cohort corresponding to being first hospitalized in period in wave 8, and so this in absolute time this will be 11. And obviously, since different cohorts correspond to different times of first hospitalizations, we will have them kind of shifted in time relative to each other. Okay, so I create this coef state variable. It's going to contain the results. And as the authors do, we are considering the weights that that enter this mu-2 coefficient. So the coefficient that is 202.6 in the fixed effect estimator. Okay, so now we need to interact our wave dummy and our period dummy. And of course, there are 5 periods, so we're going to run 5 regressions. And periods go, as we just saw in the graph, from -1. Just a reminder, its underscore is actually represents a minus. Then it's 0, 1, 2, and 3. And so this just generates the dummy of this interaction. So it's all for wave 8, or the first wave as it's called in the paper. So cohort, the first cohort, the cohort hospitalized during wave 8. And after we generate this dummy, we just run the same regression as before, just with this outcome. And the idea is basically we're gonna decompose this effect into different cohorts in different periods. And it's pretty simple, and it's kind of interesting that it actually works. After that, we're interested in the coefficient on mu-2. So this is this, again, -2 relative time period dummy. We just extract this single coefficient and add it to our results. So these are weights for the first cohort. And basically, we do this for all the time, relative time periods interacted with the wave, with the cohort dummy. And then we have 5 coefficients, and we can plot them as in the paper, but we now have done it for one cohort. And it looks exactly the same as this graph for the first cohort in the paper. And so we see that the coefficients for the relative period -1 and 0 are negative, or the weights are negative. The next two are positive, and then the last one is approximately 0, just as we have here. Though it's not that clear without the line, but basically, yeah, this is approximately 0. These two are negative, and these two are positive. Obviously, we can run very similar 5 regressions for every other cohort. So for the other 3. And then we can plot different graphs on one, different lines on one graph as in the paper. But here I show an example for one of them. So the rest would be just copy and pasting, changing some of the, those are basically just the cohort and the periods. The only thing to change that needs to be changed, yeah, is this definition of the interaction dummy, which are called flag in the code. And so this illustrates the problem with our fixed effects estimator, because now we have a mixture of negative and positive coefficients from different cohorts, different periods. And actually, that leads to the sad fact that mu minus 2, our estimated coefficient, does not really represent any meaningful or reasonable average treatment effect. So are there any questions so far? Is it clear what we're doing? Okay, if there are no questions, then we go to the third exercise. And in the third exercise, we need to replicate this table, or actually part of this table. We want these deltas that are the cohort-specific average treatment effect of the treated that are defined in the paper. And we want the weighted estimator that they have. So it's basically a weighted average of these cats. And the weights are going to be always going to be positive, and those are just the proportions of these cats in the population. And so this should be a much more reasonable estimator for the treatment effect, sort of some weighted average treatment effect, where we weight these cohort-specific effects. And we see that here, well, the results are obviously numerically different, but not very substantially. But that doesn't have to be the case, of course. If there are many negative weights, then the effect, so the difference can be more substantial. And now to estimate these deltas first, we need to run basically a very similar model, but instead of our D dummies, the relative time period dummy, we need to interact them with cohort dummy. And once we do that, of course, we're going to have more coefficients. We're going to get cohort-specific treatment effects. So that's the whole idea. Just add this interaction with the cohort, and then the delta is cohort-specific treatment effect. And then we just take the weighted average of the deltas. But to avoid multicollinearity, we have to drop one period, because in the last period, everyone has been treated. And basically, yeah, that would lead to multicollinearity here because of this interaction. And what we need to do is to generate all these sorts of interactions. I do this. Well, obviously we can write them. They can be written manually, but I was lazy. So our cohort variable is the wave of hospitalization, and they so we drop the last wave, the wave 11. So that's the last cohort, and from our specification, and yeah, we have all sorts of relative time periods. We include the same time periods we had before, I think. Yeah, except the third one. So we don't have the last time period as well. And now we just loop through the cohorts, then loop through the periods, and put them together, separated by a colon. And that is used to denote an interaction in R. And then I add the outcome variable, remove the intercept and the time dummies to get this formula here with all the interactions we want and all the fixed effects, time fixed effects here. And again, individual fixed effects will be taken care of by the PLM function. Now we have our longer formula here with the interaction terms. And of course, we need to drop the last wave. So we remove all the observations from wave 11 while estimating this. So this is the last time period. And we get our results. So these are the deltas. So we can ignore the time dummies. They're not important. We need the coefficients on these interactions. And let's compare them to the results in the paper. For example, let's take, this is cohort 1 and period 0. And the number is 2800. So we have period 0, cohort 1, 2800, 2826. That's exactly the coefficient that we get. Let's check something else. For example, for the third cohort, yeah, let's look at time period -3. This should be 591. And that's exactly what we get in the table here. So these are our weights that we get. Sorry, these are our cats that we get. The next step would be to estimate weights. And to estimate weights, we just need to look at how many observations for each cohort and for each relative time period we have. So we take our data grouped by, again, cohort and relative time period, get the number of observations for each cohort in each time period, relative time period. So the result is down here. So yeah, the first step is calculating this table, the first 3 columns. But then we take this table and again group it by just the time period, the relative time period, and we sum the numbers of observations. So this will tell us how many observations there are for the whole time period, relative time period. So I call it n sub l. And then we just divide number of observations in the cohort by the total number of observations for the time period to get the weight. And as previously, let's use the -2, the period -2. And we can see that for the with this L equal -2, we have 3 cohorts, 9, so corresponding to the waves of hospitalization 9 through 11. And here are their weights. So the first one is 0.436, and the second one is 0.403. And of course, we dropped this wave from our observations, so we don't care about this one in terms of calculating our effects. And so if we want to calculate this coefficient, so we're looking at period -2, we want to get this 353. We need to calculate the weighted average of these two cats. For the second and the third cohorts, and this is going to be the wave of hospitalization 9 and 10. And these are the weights. So here, for example, what we do here, we take the 299 multiplied by the corresponding weight of the ninth of the first cohort, which is this weight. Yeah, and then we take this effect. So again, the deltas come from the coefficients, this one and this one, and the weights from our table here. And these are just the proportions of the cohorts in terms of the numbers of observations. And since we dropped the third one, we need to divide by the sum of weights so that they sum up to 1. And actually, I have a slightly different result here, which is 355, but I think that could be due to rounding. So in this, yeah, this is the number from column 2 of the paper. So it's supposed to be this. Obviously, we've already calculated all these cats. We can use, and all the weights, so we can use all the other weights to calculate all the values in this column. And we see that for period 3, we don't get the effect because we dropped it from the data. And this is what we kind of lose due to these interactions. So any questions, comments? Yes, as you can see, the methodology proposed in the paper is really easy to implement. We just run some two-way fixed effects models, and the only thing we actually need to do is include some interactions with the cohort dummies. So if there are no questions, then I guess that's it for today. This paper pretty much replicates, which is not always the case, but it works. Okay, so I'm gonna stop